I will begin. Okay, so I will go 9 minutes late then. So, get my markers here. So I explained last time that, you know, a function is analytic if it can be represented by power series, right? So, holomorphic implies analytic. And if we wanted to talk about analytic at a point, right? We also talked about holomorphic at a point. Holomorphic at a point meant that there exists an open disk around that point on which the function's complex differentiable, right? So analytic at a point would also mean that there exists an open disk around that point on which the function is representable by a power series, all right? And so it turns out that either one of those concepts implies the other. So holomorphic at P, analytic at P. This is for complex analysis, right? So in real analysis, it's worth taking a second to mention a counterexample to this in reals. So in real analysis, you can build a function whose graph looks like this. It's 0, then it hits 0, and then it just smoothly goes like that up to 1. Right? And you can build this function. I won't give you the formula for it, but I'll just tell you there is such a function, okay? And there's a function like this, such that the nth derivative at 0 is equal to 0 for all n. So that means that the Taylor series for this function, if you look at the Taylor series for this function at 0, right, this is a smooth function. All derivatives exist. And yet, the Taylor series for this guy centered at 0, what's it look like? So it's just, you know, it's a flat line, basically. So this is y equals the Taylor series for f centered at 0 of x, right? This guy. So if you have a function which is smooth, then you can define its Taylor series by building this linear combination, the power series built from the derivatives of the function appropriately weighted, right, divided by n factorial. So this, in the real case, is an example of a function which is smooth, right? Smooth being the analog of sort of holomorphic. It means it's real differentiable and take as many real derivatives as you like, and yet it's not analytic at 0, right? So this is it's called a bump function. These are used in manifold theory for building various things. So they're actually an important function to the construction of things in manifold theory. But anyway, this is one of the reasons that real analysis is much uglier than complex analysis in a sense, because in complex analysis, this can't happen. Holomorphic is analytic, right? Which is why Gamelin wasn't so far off when at the start of everything, he just called complex differentiable analytic, you know? All right, so there's that. So let me pick at some things we skipped over just a bit. I'll do at least a little bit of some of the things we missed. I mean, I omitted. One of them I should probably do is Abels' lemma, if I can find it. Where'd you go to? I should have put a sticky note. I think it's at the start of section 5.3. Yeah, here it is. So this is Abels' convergence lemma. all right, and it says that suppose you have power series ak z to the k, all right, such that there exist positive real numbers s and m, all right, such that what? Such that the absolute value of, well, I guess I should say the modulus of ak, because that could be complex, right? The modulus of ak, s to the k, is less than or equal to m, all right, for all k, then this power series is normally convergent. Normally convergent in z in the complexes such that the modulus of z is less than s. Now, what does that mean, normally convergent? Do you remember? Everything inside the disk converges. Yes.
And there's particular points on the disk.
Well, I would say that's not quite it. Normal convergence in a set, right? So this is the set modulus of z less than s, let's say, right? So what normal convergent means is that any closed disk properly contained inside there, you have, oh goodness, I want to say absolute convergence, but it's left my mind. Golly. Just a second here. Here it is, definition 5.2.17. A sequence of holomorphic functions on a domain D converges normally to an analytic function, a holomorphic function f on D if it converges uniformly on each closed disk. So it's uniform convergence. So it means that if you take any closed disk inside here, right, like this, so if you look at that, you get uniform convergence on any such disk. And what did that mean? Uniform convergence of a series means uniform convergence of the sequence of partial sums, which means what? Which means that for each epsilon greater than 0, there exists an n independent of z, which forces the modulus of the nth partial sum and the series, well, the thing to which it's limiting, to be as small as you like. So it's uniform convergence of the sequence of partial sums on any closed disk. That's normal convergent, normal convergent. Okay, so how do you prove this Abels lemma? All right. So here's the proof. So we consider 0 less than r less than s. So consider a positive number smaller than s, right? And let q equal to r over s. So what could you say about q then? What would be less than? Nope. So q is r over s, right? So if you divide this by s, you get there q in the middle, and you get 1 up top, so it's less than 1. So q is less than 1, all right? And so for z, for modulus of z less than r, let's say, right? We have that the modulus of ak z to the k, all right, is less than the modulus of ak times, well, r to the k, right? I could put in another step. The modulus of the product is product of the moduli, and then you can pull the k out of the, here, I'll write it down rather than saying it. Duh. So this is equal to modulus of ak, modulus of z to the k, which is equal to modulus of ak, modulus of z to the k power, which then is less than modulus of ak times r to the power k by the assumption given. And then that is equal to modulus of ak times, let's see here, s to the k times r over s to the k, right? And that's 1, right? So this is less than or equal to m, I say mq to the k. Now what's this m? Where's this m coming from?
Because s to the k, well, qk is coming from the r over s, but s we know is greater than, less than or equal to m.
Right, it's assumed in the, this is a precondition of the lemma, right? It's right up here. So that's the m which was given to us. We're supposing that there exists an m such that, there exists an s and an m such that the modulus of ak times s to the k is less than or equal to m, right? So then you got mq to the k, right? Great. And what can we say about that? That the series sum over m qk, what is that? Well, that's, that's a geometric series, isn't it? See, this is just m plus mq plus mq squared and so forth, right? So that converges to m over 1 minus q, right? So it's convergent, right? That's a convergent, the series corresponding to mq, that is, this mq to the k is a term of a convergent series. In fact, it's geometric, right? Therefore, what? So we can apply Weierstrass criteria, right? So thus, by Weierstrass M test, we have that the sum, akz to the k converges. In fact, it converges uniformly, right? Well, let's see here. How did I say it? Well, is normally convergent. Well, how to say this here? It depends on how I said Weierstrass's M test earlier. Let's see here. Let me go back momentarily. Come on. Let's see here. Well, I commented that we didn't have the concept of normal convergence when we did Weierstrass's M test back on theorem 5.211. So the statement of Weierstrass's M test, we got uniformly convergent. So this is uniformly uniformly convergent on modulus of z less than r, right? But the thing is, r is what? R is arbitrary here, right?
Yes.
So that means it's just an arbitrary thing, be less than s, right? So you could definitely, pick any closed disk you like in here, right? You can make r a little bit bigger, right, like this. We could make r like this in our picture, yeah? And then we'd have uniform convergence on this disk, which then implies that we have normal convergence, series normally convergent. On modulus of z less than s. So I don't know, it's a little fussy here, like the idea, but there it is. The thing that's kind of like annoying is like you're not saying normal convergence on the disk of radius s doesn't mean it converges on s. It means it converges uniformly on subdisks found in s. All right, anyway. And that is what Weierstrass's m-test does give. So anyway, there's that. All right. So that was Abels, or Abels' convergence lemma. And that straightforward leads to, like that was used to prove that the radius of convergence, like if you look at theorem 5.3.6, which says if you have a power series, then it converges normally on a disk of radius r where r is either equal to 0, it's something finite or infinity. If you look at the proof of theorem 5.36, it basically uses this convergence lemma, and it defines r to be the supremum of, well, let me just write it down. In proof of, and then I'll stop talking about this. Proof of theorem 5.36. The radius of convergence is just constructed to be the supremum, right? The supremum of t in the non-negative real numbers, such that what? Such that, oh man, this marker stinks. Whoa, it's bad. God, that just smells rotten. Every so often. Yowzers. Modulus of ak t to the k is bounded sequence. So you see what's going on here. That is the construction of the radius of convergence in theorem 5.36. It's set up to give the input to Abels' lemma, which then powers the proof to get the convergence of the. So again, just going back to last class, the convergence of power series, either a point, a disk, some of the edges included, some not, or everything. Okay, so that's one thing. The other thing I wanted to show you today was there is also a root test. There's a root test on theorem 5.3.18 that's worth looking at. I don't have a proof in the notes. I think there's a proof on page 142 of Gamelin. But there you get a formula for the radius of convergence. I think this is known as the Cauchy-Hadamard formula. R is 1 over the limit, as k goes to infinity, of the kth root of the modulus of a sub k. So this is a sometimes useful thing, and I think that even this is this is not the Cauchy-Hadamard formula. The Cauchy-Hadamard formula is a refinement of this, which replaces the limit with the limit superior. So you have to look at the lim sup, which looks at all possible convergent subsequences of those terms. But anyway, that is getting too far into the weeds for this course here at the moment. Let's get back to section 5.4. I want to show you a calculation. So This is sometimes known as the Cauchy kernel calculation. Maybe I should do it over here. So consider f of w over w minus z. And so this calculation I'm doing, it's going to recover the formula we found for the coefficients in a power series as they relate to the integral and the derivative of the function. So let me just do the calculation, then we'll kind of walk through it here. So this is so we're looking if the modulus of z minus z naught is less than little r, which is less than rho, and the modulus of w minus z naught is equal to r, then notice that the modulus of z minus z naught over w minus z naught, well, that guy is going to be less than 1. All right, so my goal here is to start with this f of w over w minus z and to express it in terms of powers of this thing which I know has modulus less than 1. So this is going to be a lot like the calculation we did last class in terms of the substance of it, but because really I'm just adding 0 strategically, and so I added 0 strategically, right? And then I'm going to factor out something. I'm going to factor out that w minus z naught to make a 1 appear. Aha, so see that? But what you got here? Well, that's the geometric series result, right? With radius this, and a equals to 1, so I can rewrite that as a series. Excuse me. Should have got a drink or something. Oh well, too late. Sum k equals 0 to infinity of z minus z naught over w minus z naught to the power k by the geometric series, since we have the necessary condition, right? And this is what? This is for w minus z naught equals to r, okay? And what do you got? Well, then you can, this is just series, this is a constant out front, right? So you can rewrite this as just the sum k equals 0 to infinity of f of w, right, times z minus z naught to the k power divided by w minus z naught to the k plus 1. All right? But we know Cauchy's integral formula, right? What would Cauchy's integral formula tell us? It told us f of z was what? 1 over 2 pi I integral along the circle, the w minus z naught equal to r of f of w over w minus z dw, right? But hey, now I can trade, I can use this so-called Cauchy kernel. All right, I may be, well, I think this is the Cauchy kernel. I don't know, I'm not a 19th century mathematician, so I'm not exactly sure which one was which. But anyway, here this is that much we can definitely agree on, name calling aside. So that means you can swap out this fraction for this series, right? And so we've got 1 over 2 pi I summation k equals 0 to infinity f of w z minus z naught to the power k divided by w minus z naught to the k plus 1. And we're integrating, right? Integrate with respect to dw over that circle of radius r centered at z naught in w minus z naught equals to r. Now think about this. If we assume that this series of functions is uniformly convergent, right, then we can exchange the order of integration and summation. That was one of the theorems for a uniformly convergent series. The integral of the series is the series of the integrals. And so if f is holomorphic here, then that makes sense. Also, just another sort of more low-tech observation is that we can just pull the z minus z naught to the k out of this integral, because it's integral in w, not in z. So that's not, you can just pull that out. So what you got is 1 over 2 pi I, right? Then the sum k equals 0 to infinity of, what was it? The integral of f of w over w minus z naught to the k plus 1, right? dw. And my point is that, well, actually, let me be a little bit, let me bring that 2 pi I inside. That would be better. You do that too while we're at it, yeah? So sum k equals 0 to infinity, 1 over 2 pi I, like that. There, that's better. And what I'm going to do is I'm just going to, I'm trying to set us up for a comparison here, okay, of two formulas, which is this one. Oh, there's just k, right? Just k. Right? But on the flip side of things, you can derive Taylor's theorem. Just, I mean, if you assume that f of z is equal to a sum, you know, k equals 0 to infinity of like ak z minus z naught to the k, right? And let's suppose you set aside careful considerations of convergence and all that for a moment. Just suppose you're calculating formally as a freewheeling 19th century calculus, you know, scientist. You would just differentiate these things and integrate them and just assume that the order of differentiation and integration didn't really matter, you know, because it took a while for people to really appreciate that it did matter. But anyway, so if you just plug in f of 0, you'll get a0, right? And if you calculate f prime of 0, you'll get a1. And if you calculate f prime prime, excuse me, z naught, not 0. And f prime prime of z naught, well, that's going to be, you know, 2 times a2. And if you calculate, just directly calculate the nth derivative at z naught using term-by-term differentiation, out pops n factorial times an, right? So therefore, you know, the nth coefficient, or if I used k instead of n, the kth coefficient would be the kth derivative evaluated z naught divided by k factorial, right? So my point to you is we could just as well write this as equal to the sum, you know, k equals 0 to infinity of the kth derivative at z naught divided by k factorial times z minus z naught, right? And if you do this, what does this mean? What happens? What do we see? We see that the coefficient of z minus z naught we could either write in terms of this integral or in terms of these derivatives. In other words, Cauchy's generalized integral formula is a natural consequence of this Cauchy kernel calculation paired with the assumption that, differentiation and integration exchange orders. See, because this equal to that is Cauchy's generalized integral formula. See it? Okay. So I think that's a very neat calculation. I try to share that in this course because I think it's not, a lot of these proofs are kind of one-offs, but actually the calculation in this proof is something we need for examples, all right? So let me move on here. So other things that follow from holomorphic equal to analytic. Corollary 5.43 says that if you have the kth derivatives matching for k greater than or equal to 0, then the functions are equal. So if you have the derivatives and the second derivatives and the third derivatives and all the way on out, if they're all equal to each other, well then, of course, you can then build the functions being equal to each other, right? Because they're generated by their Taylor series, and consequently you get equality of the functions. That is kind of like a more, we had, what did we have before in like calculus 1? Remember the calculus 1? Calc 1, with calculus 1, what did you have? If you have f prime of x equals to g prime of x, that implies what? F of x is equal to g of x plus c, right? And if you also know that f of, let's say x naught is equal to g of x naught, right? That implies what? That implies that, f of x is equal to g of x in this case, right? So this was for all x in some connected interval, a subset of the reals, right? So this corollary is saying something a little bit different. What it's saying is that if you have, consider this, if you have f prime, if you have f of z naught equals to g of z naught, right? And you have f prime of z naught equals to g prime of z naught. And you have f prime prime of z naught equals to g prime prime of z naught. And so forth and so on. If you have the nth derivative of z naught equal to the nth derivative of g of z naught, if you have the derivatives are matching for all orders at one point, then f of z is equal to g of z. Now this is, what's the precondition here for f and g analytic at, z naught. And really we should say f and g analytic on D containing z naught there, that's better. So the top part, I'm just reminding you, calculus 1, we have a theorem that if we have the derivatives are equal for all points, then we get the function on a connected interval, we get f of x is equal to g of x plus a constant, right? Remember that result?
How did you get f of x naught plus g of x naught if f of x and g of x?
So if in addition to that, if there exists a point at which those functions are equal, that means the constant's 0, so the functions match up. But you notice that theorem in calculus 1 is much greedier in the sense that you need infinitely many conditions on the derivatives.
Yeah.
This corollary 5.43 is saying that if you have this, I guess it's again infinitely many conditions, but it's just at one point, right? So if you know that all of the derivatives match up at that one point, then it forces them to be equal on all of D, of that domain D. Now, so, and that leads into the corollary 5.44, which is that the radius of convergence of a power series is the largest number R such that f of z extends to be holomorphic on the disk. So So what corollary 5.44 is saying, like, is what I was observing in the examples last time, which is that if you have a function which has got trouble points, right? Well, and if you have a function with trouble points, I'm trying to say, suppose you draw a picture. F of z, is holomorphic on D, right? But D is missing some things, right? So D is missing some things. So here's a picture. Maybe D is missing this point and this point, right? Here's another point. These are, let me call it Z, Z1, Z2, Z3. Okay, so Z1, Z2, Z3, not an element of D, right? So these are like singular points, we would call them, for the function, all right? Then what the corollary, shush, quiet, I said quiet to you. What corollary 5.44 is saying is that if you expand this function as a power series about a point, right? Suppose, this point right here. If this is your center for your power series, it says that the radius of convergence will be as big as it can be. And in other words, it will extend all the way to there, to z there, right? On the other hand, if you take this function and you expand its power series over here, then probably my picture, maybe you can't tell very clearly, but then z1 is going to stop it from getting bigger. But see, the radius of convergence, remember those old ads for the Army? Be all you can be? It's like that. It's as big as it can be. I guess the Army just says now, like, be whatever you define yourself to be, so it's a little different, but do I have to edit this? It's on the bubble these days. Let's see here. I think it's safely hidden in a complex analysis lecture, which should be okay. One of the 40 people who watches this object. Let's see here. Okay, so anyway. Now, so I'm trying to give you more insight as to how power series for complex functions work today, right? That's kind of the theme of our lecture today. So something else I need to tell you about. Isolated points. What's an isolated point? So if U is a subset of the complex numbers, let's say, and Z naught is an element of U such that there exists, let's say, epsilon greater than 0, for which Z such that the modulus of Z minus, Z in U such that the modulus of Z minus Z naught is less than epsilon is just equal to Z naught, then Z naught is an isolated point. All right. Is it a point of convergence? I don't guess I would say that. Let me just double check on my definition of isolated point here. If I can find my way over to this page. Come on. Where'd you go? email. I was reading through this beforehand, and I found the definition of isolated point somewhere, and now I can't find it. But I believe that this is a good enough definition. But theorem 5 point, and sorry I'm jumping a little bit through the chapter here. I will probably have to make another lecture after this to clean it up. But I'm trying to get to something here today. So theorem 5.7.13, if D is a domain, F is an analytic function on D, which is not identically 0, the zeros of F are isolated points in D. So what do I mean by that? Zeros, what's meant by that? The zeros are isolated points in D. I don't think I really mean what I have written above. I mean, so the picture of what's going on above is maybe U looks like this, right? But then it's also got like some stragglers out here, right? So this would make Z not an isolated point because like most of U is over here, right? So this point, you could look at the disk of radius, epsilon, about Z naught, and all that would be in there is what? Just Z naught itself, It's isolated from U. So the theorem here, 5.7.15 on page 123 of my notes, it's saying that the, my bad, wrong, I just flipped the page. 5.7.13 on page 122, D be a domain, F an analytic function on D, which is not identically 0. The zeros of F are isolated points in D. What does that mean? See, that's not saying that the zeros have to be outside of the domain. That's not at all what's meant there, right? So this is not the right definition to be thinking about. That use of the term isolated points means with respect to each other, right? If you look at the set of zeros, they have to be separated, Another way to say this is zeros of, analytic function, non-zero function, are not infinitely close together, okay? Like, you can't have the situation that here's the complex plane and here's, the zeros of your function. There's one at 1, there's one at, a half, there's another 0 for your function at 1/3, right? You couldn't have a set of zeros be like 1 over n, such that n is, the natural numbers. Like this could not be a set of zeros for, f of z not identically equal to 0 on D. I say non-zero function, I mean it's not the zero function. Of course, the zero function has the whole complex plane as its set of zeros, and so then the zeros are...
No, my question is, what do you mean by 0 on a complex plane?
What do I mean by 0 on the complex plane?
I think of the origin things, I think of it as 0.
Oh, okay, so that's a good question, and so this is part of the casualty of me skipping ahead in the notes here a bit, and that's because I haven't defined 0 yet, right? So let me define 0. That's a good question. So this is the start of section 5.7. Definition, let F be analytic and non-zero near z equals to z naught, all right? Then we say F has 0 of order n at z naught, all right, if f of z naught is equal to 0, f prime of z naught is equal to 0, all the way on out to the nth derivative, n minus 1th derivative at z naught is equal to 0, and the nth derivative at z naught is not equal to 0. A 0 of order n equals to 1 is called simple 0. All right. N equals to 2 is called a double 0. So this is what I mean by zeros of an analytic function. So what is that? There's a factor theorem, all right? What's the factor theorem? So the factor theorem for analytic functions says this, all right? So factor theorem says this, if f of z has 0 z naught of order n, then f of z is equal to z minus z naught to the n times g of z, where g of z naught is not equal to 0. And here g of z is another analytic function. This is the factor theorem, right? For polynomials, I mean, we're most familiar with it for the case of a simple 0, right? Which is we just factor out a simple, just one factor, but that's that. So it takes a lot of different pieces woven together in this chapter, but ultimately what Gamelin shows is that the zeros of an analytic function are not infinitely close together, all right? They have to be isolated points. And what's fascinating is that then gives us the following result. That leads us to the result that theorem 5.14, which I'll say here, says if f and g are analytic on domain D, and if f of z is equal to g of z for each z belonging to a set with a non-isolated point, then f of z is equal to g of z for all z in D. All right. So what does this mean? So like last class, I gave you formulas for cosh, sinh, sine, exponential, all those things, right? And if you look at those formulas and you study calculus 2, you'll find that those formulas all restrict to the ordinary power series formulas for those functions, sine, cosine, cosh, sinh, exponential, on the real line, all right? So the real line is an example of a set, right? if we look at the complex numbers, right, think about the whole set of complex numbers, d equal to the complex numbers, right? And if you think about the real line, right? So this is just what? Imaginary part of z equals to 0, aka the real axis, you know? This is certainly a set with a non-isolated point, right? Because if I pick this point, and it's talking about isolation with respect to the set itself, yeah? So it's a subset of D which has an isolated point, a non-isolated point with respect to the subset, right? Non-isolated with respect to the complex plane is a tautology almost. Like every point is not isolated from any point in the complex plane is not isolated, is not an isolated point for the complex plane, of course. But so any point on the real line has infinitely many other points on the real line close to that point. You can't separate them. You can't, right? You cannot separate them.
So, like, would it be like one of those sets where it has like points like flying off? Like that's an isolated point.
Yeah.
There's no points if you're not close to it.
So the good example of a set with isolated points is like the domain of a sequence. Natural numbers are isolated, right? So like I think of isolated points, I think of like discrete things. But my point to you is this says that, so hypothetically, imagine you're trying to generalize cosine, sine, exponential, any of these functions, right? If you wanted to build an exponential for the complex numbers, which reduces to the real exponential, there's only one choice. See, because if it reduces to the real exponential, right? It has to be what I wrote last class, because this thing, e to the z is 1 plus z plus 1/2 z squared, so forth and so on, right? That restricts to e to the x. You know, on the real axis, let me call that thing s. And so if you tried to give a different definition for the complex exponential, right, you wouldn't be able to do it, because whatever your different definition for the complex exponential, suppose you had g, suppose this is f of z, right? And suppose you had g of z, something else, right? Such that g of x is equal to, e to the x for x in s, right? So in other words, this g and the complex exponential both restrict to the real exponential on the real line. So they're equal on a set not containing an isolated point. Therefore, this is equal to that. It's the only possible extension of the exponential to the complex plane. Likewise, complex sine, complex cosine, all the things I've defined last class, they're inescapable because of this theorem. Another way to understand this, I cannot emphasize how shocking this theorem is. In linear algebra, we learn that, well, linear algebra, first of all, is an incredibly strong structure. Like, to assume linearity of a function, that means that the formula is just matrix multiplication. That's very, very simplistic. So for a vector space of dimension n, if we want to fix a linear map, if we say how the basis is mapped, we fix the map. In other words, despite the fact that a vector space has infinitely many points, if you tell me how n points map for a vector space, you've completely fixed that linear map. This says something similar. For the entire complex plane, if you have a function which is holomorphic, right? And that function, if you tell how the function behaves on a set not containing an isolated point, you've fixed the action of the complex function to the rest of the domain.
It kind of makes sense, because then you can just build a function from like vertical lines, essentially,
Maybe.
If you have a function restricted to
But
well, this is specific to
So then here's the problem, right? Caution. So this is the thinking that people like Euler came to understand. This is called the principle of permanence that, well, let me just say that. And here's a quote from Euler in 1749. We see, therefore, it is essential to the nature of logarithms that each number have an infinity of logarithms, and that all these logarithms be different, not only from one another, but also different from logarithms of every other number. That doesn't seem to square well with what we're saying right now, does it? Like, how can there be? There's just, if you have, let's see here how to say this. So f of z equals to log z, right? That's for what? For z in the slit complex plane, right? So c with 0 to infinity removed, yeah? And so if I draw a picture of that, right?
Is it 0 to infinity or minus infinity to 0?
Oh yeah, sorry. I usually do that, don't I? I'm in the negative axis, whatever our notation is for that. So that's the d in this set, right? So and then let's see here. And then in the real analysis, you have what? You have, let's say, natural log of x. That's a function, right? This is, so if we take log for z equals to, x in 0 not included to infinity, right? We have, indeed, the principal logarithm of x is just equal to the natural log of the modulus of x plus I arg x, right? But the argument of that is 0, so this just breaks back down to log x, right? So the principal logarithm, principal logarithm agrees with the natural log from real analysis on the positive real axis, right? Yeah. Is that a set with a non-isolated point? Yeah, I think it is, right? Here's my quote-unquote S, yeah? Yeah. So any other extension, right, of the real log should agree with this, right? Yeah. Be careful. On what set?
On everything that's not that square.
Yeah. Is that what the theorem says, though?
Yeah, so it should agree.
On D, right? So what if we looked at a different branch of the logarithm?
They're not going to agree because they're going to be a flip sign somewhere, right?
Yeah, I mean, so I guess in the worst case, I mean, if you look at the, I called it logo, the one that has the jump at 0.
Yeah.
But if we look at log alpha, right, this one, so we're removing the thing t e to the I alpha, right? So you're removing, we're chopping out the ray at alpha, wherever that is, Let's suppose it's over there. So we've lost that. So we could still compare. We should still have that. See, we should still have, if S is not the ray that we're deleting for the branch cut, we should still have that log alpha of x is equal to natural log of x, right?